Hello everyone, welcome to MG Chemistry Tutoring. So in this particular question, it says you are given two solutions, one containing a weak acid, HA, and the other a weak base, BOH. The Ka for the HA is 1.8 times 10 to the negative 5, and the Kb for the BOH is 3.6 times 10 to the negative 6. In the first part of the question, it says calculate the pH of a zero point 0.1 molar solution of HA. Dissociation of the HA, the weak acid. So we have it dissociate into H plus aqueous plus A minus aqueous. We're going to do a nice table for this. So we know that the initial concentration is 0.1 molar of the acid, and the change is going to be minus X. So at equilibrium, we have 0.1 minus X. And for the initial, for both of these, is going to be 0. And the change is going to be plus X for both of them. So at equilibrium, they're going to be both X. And then we're going to find the equilibrium expression for this weak acid. That's going to be Ka. And we have the value of Ka that's given to us. It's 1.8 times 10 to the negative 5th. And that's going to equal to the concentration of the H plus times the concentration of the conjugate base divided by the concentration of the HA. So we can actually plug these values in here because we actually have what they are at equilibrium. So for the H plus, it's just going to be an X. So we'll just plug it in here. So this is actually just X. And then it's going to be X for this A minus as well. So times X. And then we're going to make an approximation here and say that that's very close to 0.10 to avoid using the quadratic equation. So now we can actually just cross multiply. So that's going to be x squared is equal to 1.8 times 10 to the negative 5th times 0.1. That's 1.8 times 10 to the negative 6th. And then we'll square root both sides to solve for x. So our x value it's equal to 1.34 times 10 to the negative 3 molar. So for this one, we know that that's the concentration of the hydronium ion. So because that's the value of x, so we can just plug it in here. And then that's also the concentration of the conjugate base. And then that's how much we subtract. So at equilibrium, we would have these concentrations here. Now, to solve for the pH, what we have to do is we're going to take the negative log of the H plus concentration, and we know what that is already. So that's just negative log of 1.34 times 10 to the negative 3. So that means that our pH is going to equal 2.87. So we have the concentrations at equilibrium already. So what we're going to do now is we're just going to take these values at equilibrium, and they're going to be our initials, just to make this easier. So we're going to subtract this first. So 0.1 minus 1.34 times 10 to the negative 3. That's going to equal to 0.09866. And then we'll just put that new value up here, 0.9866. And then that's going to be in moles. The reason that's in moles is because molarity is equal to number of moles divided by volume. And they say that it's within the 1 liter solution. So whatever number we put up here for number of moles, in this case that value, it would still equal to a molarity equal to 0.09866 molar. And then get rid of this. So this is the new, or this is the concentration at equilibrium, and that's moles as well. And likewise, that's the same value for the conjugate base in moles. And then for part 3, it says that we have this much being added. So we have to say that plus 0.050 mole is added. So now, after the reaction has taken place, we have a new value of H plus. So we're going to add this plus this. And that's going to equal to 0.05134 mole. So that's our new value that we're going to use, because we have to solve for the pH now of this new altered solution. So we know that that's the number of moles. So the concentration of H plus is going to equal to the number of moles divided by a 1 liter solution. So that's 0.0505134 moles per 1 liter. And that's the same thing as 0.05134 molar. So that's the concentration. And we know that to solve for the pH, we have to take the negative log of the H plus concentration. So that's going to be negative log of 0.05134 and our pH is going to equal to 1.29. So for part 3, the pH, the new pH is going to be 1.29 after adding 0.050 moles of H plus. So the solution became more acidic because the pH number decreased. So now let's go back to part 2. So for part 2 of this question, what we're going to do is we're going to write out the dissociation of this weak base. So this is a weak base because they give us a Kb value. So this dissociation is going to be BH plus plus OH minus. And they're all aqueous. And we're going to do a nice table for this as well. So it says that starting concentration is 0.20 molar. The change is minus X. So at equilibrium, we have 0.20 minus X. We'll get rid of the unit for now. And initially, we have 0. The change is going to be plus X for both of these. So at equilibrium, we have X and X. We know that the equilibrium expression for this weak base, Kb, is equal to the value is given to us. So 3.6 times 10 to the negative 6. And that's equal to the concentration of B plus times the concentration of the OH minus divided by the concentration of the BOH, weak base. And at equilibrium, these concentrations are going to be at equilibrium. So we actually have them already here. We're just going to replace them with the variables. So this is just going to be X. And then this one is also going to be X. And then we're going to approximate that 0.2 minus X is about 0.20. So we don't have to use a quadratic formula. Okay. So now we can just cross multiply here. That's X squared, X times X. And then this times that is equal to, so 3.6 times 10 to the negative 6 times 0.2. That's 7.2 times 10 to the negative 7 molar. And then we'll square root both sides to solve for X. So X is equal to 8.49 times 10 to the negative 4 molar. So now we solve for X. Now we can just replace it here. 8.49 times 10 to the negative 4 molar. Same thing here. We replace the X. And then replace the X here. Okay. So those are our new concentrations at equilibrium. Now to solve for the pH, we have to do 2 additional steps. So we don't have an H plus concentration, we have an OH minus concentration. So what we're gonna do is we're gonna do the POH. So the POH is equal to the negative log of the OH minus concentration. And we have the OH minus concentration. The OH minus concentration is just the value of X we solved for right here. So that's 8.49 times 10 to the negative 4. So that means that our POH is equal to 3.07. And we know that pH plus POH is equal to 14. And we have POH already, which is 3.07. So we subtract both sides by 3.07, and we know that our pH is equal to 14 minus 3.07. Our pH is therefore equal to 10.93. So that's the pH for part 2. And now we'll move to the last part of this question. So for the last part of this question, it says if 0.030 moles of OH minus ions are added to 1 liter of the BOH solution, calculate the resulting pH. So what we're going to do is we're going to do a second ice table. So now we're going to take these values and then put them as our initial values just to make this easier. So we'll first subtract this 0.2 minus 8.49 times 10 to the negative 4. That's going to equal to 0.9199151. So we're just going to replace this up here, get rid of that. So it's 0.199151. And then this value is going to go up here. And then this value is also going to go up here. And these are going to be in terms of moles, because this is a 1 liter solution. That's why. And we know that that's how many moles we have. So it says that this many moles of the OH minus are added. So we're going to say plus 0.030 moles of this added. So now after the reaction has occurred, we know that we're just going to add this plus this to get the end result, number of moles of OH minus. So 8.49 so we have at equilibrium, not at equilibrium, but after the reaction has occurred, this value of moles for OH minus. So concentration of OH minus is just going to equal to 0.030849 moles per 1 liter, which is just the same value, but in terms of molarity. So now to solve for the POH, we take the negative log of the OH minus concentration. So that's going to be this value, 0.030849. So the POH is equal to 1.51. And here they're asking for the pH. So we know that pH plus POH is equal to 14. So we have the POH equal to 1.51. So we just subtract 1.51 from both sides. So the pH is then equal to 14 minus 1.51. That's going to equal to 12.49. So that's the pH after we add 0.03 moles of OH minus.